All right, guys, so we're going to do the buck boost test on the Hammond transformers. First thing you're going to do is you're going to pick out one of these boxes from the cabinet. You're going to make sure that you're not drawing on the sides of the unit. We're going to put some painter's tape on the side to put the names of X1, X2, X3, X4. These are randomized inside the box. I'm going to open up one of these boxes and show you that these aren't exactly X1, X2, X3, X4. They may be flipped. This may be 4, this may be 3. They may all be the same. They may be randomized throughout. Okay, there's a big ass sign on the bottom of this, only the 1/4 amp fuse. Okay, so please only use that fuse. Don't grab a 5 amp fuse from the PLC trainers. If you, invariably you're going to blow one of the fuses. And if it's a 1/4 amp, then the transformer inside this unit will be fine. It's a 5 amp, smoking a pancake, and you've just bought yourself a Hammond trainer. Okay, so those units are going to have these fuses inside. So we're using the 1/4 amp MDL fuses now. We were using these glass type fuses, but we were finding that they were vaporizing. You guys were vaporizing them, so we're finding that these ones here are working a little bit better. Okay, still 1/4 amp. Okay, so those ones go into here. So you're making sure that each of your fuses are good. Replace them in the trainer. We had made use of some breakers, mini breakers here instead of the fuses. That one's stuck, and they were vaporized as well. So we're sticking with the fuses here, guys. In addition to these fuses, we're going to make use of, I'm going to finish this off in 2 seconds because I can't get that in. In addition to that fuse, we're coming off of this breaker. This breaker is from 1969. It is only rated at 3 amps. It's clearly stating that it's there for the transformer station. Okay, over here we have a 15 amp breaker. Okay, this is for your motor controls. Okay, you can see the rating of the breaker here. If you use this breaker with this trainer, then smoking a pancake. Okay, it's going to allow too much current to come through. So we're going to make use of the 3 amp breaker, and we're making sure that we're using the 1/4 amp fuse on each of these inputs on the primary of the transformers. That 3 amp breaker has 3 connections here. So we got line 1, line 2, and line 3. There's 2.8 available in the room. Okay, so you'll have 3-phase 2.8 available here, but limited to 3 amps on this breaker. Okay, again, you can easily discern the difference between the motor control station and the transformer station. This is the motor control station at 15 amps. It has a neutral and a ground there. So the transformer breakers just have the 3-phase coming out. Why do I have this tone to my voice? Because you guys keep vaporizing the transformer trainers. So make sure you use the right breaker. Make sure you're looking to see that you've done the appropriate connections on the transformer, and make sure that you're using the 1/4 amp fuses. And that way we can keep these transformer trainers working longer rather than you guys vaporizing them every class. Okay, next step, we're going to take an ohm meter, and we're going to look at the resistance of these windings and make sure that a previous student hasn't smoked these windings inside the box. Okay, so within the box, we've got 3 single-phase transformers. You can see that the rating of these guys are 2.8 on the primary, and the secondary we have 2 separate windings. They have 120 volts out, so the ratio there is √3 to 1, right? 1.73 to 1. 2.8 in and 120 volts out. Looks like we got 0.4 amps that they're rated for on the secondary. Obviously 60 hertz because we're in Canada. And another thing to notice is the VA, they're 100 VA transformers. We're not connecting up a load to these guys. We're just looking at the voltage that comes out when we connect them up in single phase or 3-phase configurations. And so we don't have to worry about having too much VA for lighting loads or anything like that. Those connections come out and then they come to the front of the unit. So these terminals right here that you see for your primary and for your secondary, they're just soldered in on the back of the unit there. Okay, but they are randomized in that they won't exactly be like these ones will be the same, right? H are clearly marked, H1, H2, H1, H2, H1, H2. Primaries are all the same polarity, but the secondaries, this one might be X1, this one might be X2, this one might be X4, this one might be X3. And again, they may be randomized between the transformers, and they're definitely like specific windings, like this will be X1 and X2, or X3 and X4, right? We're just not sure which one is which because they've been randomized. So the next step we're going to do is we're going to check the resistance of the winding, make sure that everything's good with the actual transformer. Like we can see that, like looking at the transformers, they look good. Nobody's actually cooked those windings there, but we'll see with the resistance value whether they have identical resistances between the secondary and primary windings. And then once we've got, we're confirmed that this trainer is in good order, then we're going to start doing a buck boost test. Okay, so we've grabbed a multimeter from the back of the room. We've got this on the ohm setting here, we're on the voltage and the common here, and we're going to test out the primary here. We'll check out what the resistance is. So it looks like we got 7 ohms on the primary. Let's see if they're all the same. So clearly that primary is good. Let's see if it's identical to this guy. Okay, 7 ohms on this guy. And on our third transformer, 7 ohms, right on. Okay, so we can see that the primaries are good and they all have equal resistance values. Beautiful, okay? This doesn't tell us anything about the polarity. The polarity is already shown here, but in this meter we have a 9-volt battery. So a DC 9-volt battery is not going to show us polarity on here. All we're seeing is that the windings are actually good. Let's take a look at the secondaries now. So secondary here has 10 ohms. So higher resistance. That's interesting actually, because you would think that on the secondary, if you had less turns, you would have less resistance. But that's not the case with these guys. Let's see whether that winding is smoked compared to the other ones. Smoke meaning like it has a higher resistance. Okay, that's 7.6. Okay, so you can see that these transformers have been beat up quite a bit, right? So that's 7.6. These ones we would like to have the same resistance value, but previous students have shorted out the secondaries, and in doing so have affected the resistance of the windings. There's 10 ohms there. Okay, let's see what this resistance is on the second winding. 11 ohms. Okay, so 10 ohms seems to be the norm. Third transformer, first winding's 10. And final one is 11. Looks good. So the only anomaly right here is this winding right here on the secondary. It's only giving us 7.6. Why is it? I have no idea why it's doing that. I'm thinking abuse, compared to the 10 ohms that we're seeing on each of these guys. I also do find it interesting that this is a higher resistance than the primary. I would have thought that the primary would have had a higher resistance because it had more turns. But again, there's 2 different forms of resistance in these transformers. Remember, there's physical resistance that we're seeing right here, and then magnetic resistance being XL or inductive reactance. You only see that inductive reactance once we have the AC flowing within the windings there. Okay, so this transformer trainer is good to go. Okay, so we want to do those tests prior to even juicing up the transformers. So take the time, check the fuses, check the windings, make sure everything's cool. We're writing down those resistance values. And you can see that I put some painter's tape here so I can put my labels for my secondary windings now. Okay guys, so first thing we're going to do is we're going to put the feed. So you see I have my 3 amp breaker over here, and I'm bringing line 1 or the A phase to H1, and I'm bringing line 2 or the B phase to H2. As we do each of these transformers, I want you to keep this polarity the same for every transformer. So we're going to do this buck boost or additive subtractive test on each of the transformers. It's essential that you keep this polarity the same for each transformer. If you flip that polarity, then all your secondary polarities change as well. So keep this polarity the same so we can mark out X1, X2, X3, X4 there. So I'm just going to arbitrarily do this. I saw continuity between these guys. Not just because on the Lamacoid, because there's a diagram there, but because I saw continuity there with my ohm meter. So I'm just going to arbitrarily say that, all right, everything goes from 1 to 4 there. Most likely not the case, but that's where I'm going to start off. Okay. Next thing I'm going to do is I'm going to put a jumper between X2 and X3. So you can see that we're using these shrouded leads here. So you can see these guys, there's the shrouded leads, compared to the older leads, 2 seconds. The older leads would have been like this, right? These are the older ones that we're using. Not as safe because they have obviously the metal that's open there. We're not going to be getting our fingers anywhere near these guys, but these ones allow us a little bit more safety in that they have the shrouded leads, the metal's inside there. Okay, so I'm going to jumper X2, or what I think is X2 to X3. So I'm going to series up the secondary of the transformer there. Okay, then this is a little bit messed up. I'm now going to connect up the primary to the secondary. So it's messed up in that you don't usually connect up the primary to the secondary, but we're going to create something like an auto transformer where we have the primary windings and the secondary windings in series. So I'm going to put X1 to H2. So what I think is X1 to H2 here. Okay. And then when I juice it up, I'm going to take the voltage between the two open terminals. Now, one of the terminals is clearly open right here. The other terminal that's open is H1. So I'm going to be taking a voltage reading between X1 and between H1 and X4. Just to be clear, I'm not shorting out the transformer here, right? Because I have two open connections here. So I've created a series connection between the primary and the secondary, but I have not short-circuited the entire transformer. If I turn this guy on without putting the meter into the circuit, then you can see that the breaker holds. Okay, so I'm not shorting out anything there. I have my power off now. I have my meter on AC volts, and I'm going to check the voltage between the two open connections here. Okay, your voltmeter is a high impedance load, so it's not going to short out anything. Okay, so let's see what the voltage is there once we juice this up. Maybe I'll turn the unit on, hang on. There we go. At the end of the line, we've got a 3-wire that feeds here. So that is not what I was looking for. I was looking for a disgusting voltage that to come out. And this is actually the worst case scenario if you're a student, because I'm looking at the difference between the windings there, between the primary and the secondary. I'll stop in 2 seconds and show you a diagram of what I'm doing. But right now, and you can see that my hands are nowhere near the circuit. So I got 2 8-volts between those two open connections. If I turn this off and then check my primary winding, right? So my primary winding would be H1 and H2. I have 2 8-volts coming into the circuit. So there's 2 8-volts on the primary there. But then once I've series up the primary and the secondary, the sum of the voltages on the primary plus the voltages on the secondary is also giving me 208 volts. So that means that I must have these two canceling each other out, right? So this voltage is not even in the circuit, and the only voltage I'm seeing is my primary voltage. Again, probably the worst case scenario for a student. It's better if it just, it's the additive voltage and we see that the primary and the secondary voltages are adding together. We see it on the meter, but that's clearly not so. So how are we going to fix this? Let me stop for 2 seconds and let me show you a diagram of what I've connected, and then you'll see why this is 2 8-volts. Okay, so if you're looking in the manual or the handout that I provided you with you, then we're on page 5 here. So let's scroll down here. And I've got a diagram here. So that's our subtractive voltage. That's our additive voltage. Where's the diagram for the 2.8? There we go. Okay, so what's happening here is that we have one winding on the primary, and we have 2 windings on the secondary, right? We have H1 and H2 on the primary. Then we have X1, X2, X3, and X4. And we're trying to determine the relative polarity. So you can see that on this diagram, I've put a dot on H1 and X1 and H1 and X3, saying that they have the same instantaneous polarity. So we're trying to determine which one is actually X1 and which one is actually X3. And so we're connecting up the primary and the secondary together. So in this diagram, I've got H2 going over to X2 right here. So I thought I had H2 going to X1, but in fact I've got it going to X2. So what's happening here is that I've got 1 meter lead right here. So there's my voltmeter right here. And I have 1 meter lead here, and I got another meter lead right here. So all we're going to do is we're going to start at 1 meter lead. We're going to go through the circuit and see how we pick up the voltage. And I like to use arrows to show, like to denote like the instantaneous magnetic fields. So from this meter lead right here, it looks like we're picking up 2.8 volts. I'm saying we're picking up 2.8 volts because we're going in the same direction as that arrow. Okay, then following that same circuit, we're coming from there. And that 2.8 again is coming from line 1 and line 2 from our source voltage. Okay, then we're coming over here. So we've got 2.8 volts so far. And then as we come along here, then we're going to lose 120 because we're going in the opposite direction of the arrow that we had on the primary. So we have 2.8 minus the 120. And then when we come over here, then we're going to pick up 120 again because now we're going in the same direction as that arrow. So as we went through that circuit from this point, 2.8 minus the 120, right? Opposite direction through this winding. So minus the 120 plus the 120. Well, then the voltage between these 2 points is going to be limited to this 208 volts. Because we have this connection here and we've got the polarities of the secondaries opposing each other, these two 120s are canceling each other out, leaving us with the 208 volts. Again, probably the last thing that we want to start with as a student. It would have been better to actually see the additive voltage or see the subtractive voltage. So we've got to do one thing to change this. So let's go back to the lab and we'll see which one thing we need to change on our transformer. Okay, so one of the windings must be backwards, right? Either this one or this one, because at the moment they're pushing against each other. The voltages are the exact same and opposing each other and canceling each other out. So I'm going to do this. I'm going to just arbitrarily change these two. I'm going to say that's 4 and that's 3. Okay, so I'm choosing one of the windings and I'm saying, all right, that's no longer 4, it's 3. That's no longer 3, it's 4. Power's off. I'm taking that jumper that I had from what I thought was X2 to X3 and moving that over to this terminal right here now. Okay, I'm still have the connection between the primary and the secondary. I've got this connected up in what I hope is an additive voltage in that the primary and the secondary voltages are going to sum together. And I'm going to take the voltage now between H1 and X4. Oh yes. Okay, so now we've got the additive voltage, 458 volts. Okay, so where's that voltage coming from? Well, that voltage is coming from the fact that I have 2.8 volts here, and I got 120 and 120. All those voltages are summing together. So 2.8 plus 120 plus 120. Okay, so that's why we're seeing that large voltage there on the meter. So this is our boost connection, or the additive connection. Okay, let me stop here for 2 seconds. I'll show you the diagram that corresponds to this connection. And before we show that, all I did there was I wasn't getting the appropriate voltage, so I arbitrarily changed the 3 and the 4. I could have changed the 1 and the 2, but I just arbitrarily changed one of the windings and flipped those connections there. Okay, let me show you the diagram for this connection. All right, guys, let's take a look at this diagram. We'll try and figure out the additive voltage. Now, if you're paying really close attention, you'll see that this is actually a mirror image of what I just showed you in the lab. Not intentional, but I'm just looking at this, and there is the difference between what we just did in the lab and this diagram. It's still going to show us the additive voltage, but I should point out the changes here. So we had a jumper between H2 and X1. Well, in this diagram, I have my voltmeter between H2 and X1. Okay, then we had the voltmeter between H1 and X4. Well, that's where I have the jumper on this diagram. Okay, so just to call out that little change there, we should still see the additive voltage, but it's not exactly what I had there in the lab. Okay, so let's see. I'm going to arbitrarily put in some lines here to denote a magnetic field. Okay, so just an instantaneous magnetic field. Of course, the magnetic fields are bouncing back and forth 60 times a second, but I'm just showing that H1 and X1 have the same relative polarity, and H1 and X3 have the same relative polarity. Okay, I've got my meter connected up right here, right? So I've got 1 meter lead right here, and I've got another meter lead right here. Okay, and then let's walk through this this circuit here, guys. Okay, so we're going to start at this meter lead right here, right? So we're starting right here, and it looks like I'm going against the arrow, so I'm losing 2.8. And then I'm coming over here, and then I'm losing 120, and then losing 120. So I've got negative voltages all the way through. But in starting from this point, I've got negative 2.8 plus negative 120 plus negative 120. So those voltages are all going to sum together. If I start at this point right here, which would have made a little bit more sense, then it looks like I am picking up 120 because I'm going in the same direction as the arrow. So I have 120 plus 120 to give me 240. And that connection is coming up here. I got 240 so far, and now I'm adding the 2.8 because I'm going in the same direction. Okay, so in this case, with the additive voltage, I'm going to get 120 plus 120 to give me 240, plus the 2.8 to give me a total of 448 volts. Is it going to be exactly 448 volts? No, it's actually going to be a little bit higher, and that's because I only have the voltmeter. I only have a high impedance load in the circuit. So I haven't actually completed the circuit. I don't have any current flowing, so the internal resistance of the windings isn't going to come into play. So we're expecting to see the additive voltage. We're expecting to see that this voltage 120 plus the 120 gives us 240 plus the 2.8 gives us a total of 448 volts. Okay, let's go back to the lab and see if that's what we get. Okay, so hopefully it's making sense to you. Let me turn off the power here. I was looking at the sum of the primary and both the windings on the secondary there with my my voltmeter. But what if I just want to look at the voltage between one winding on the primary and one winding on the secondary? Then I'd be looking at the voltage between H1, so I'm still connected to H1, and I'm going to go to X2. So X2 is right here. So the voltage that we saw before, sorry, I'm all over the place. The voltage that we saw before was 460 volts, right? So that voltage, we were thinking 240 plus 2.8, we were thinking it'd be 448. We're seeing a little bit larger voltage there. Okay? The voltage between the primary and one winding should be 240 plus 120, should give us around 360 volts. So I'm going between H1 and X2, and we'll see what that voltage is. There we go, 330 volts. Okay, I was expecting 360, with a little bit less voltage there. Okay, remember that there is no current flowing here. This is just a pressure or voltage that we're seeing, and we're seeing the voltage between one primary winding and one secondary winding, and they're summing together, or we have the additive voltage. All right, guys, next thing you're going to see me do is the subtractive connection. So let's walk through that one together. So for this guy, again, I'm going to put the dots here for H1, X1, and X3. We'll put our instantaneous polarity here, denoted with these arrows. Okay, this one actually matches what I'm doing in the video, in that I have a jumper here between H1 and X1, and my meter is going to be between H2 and X4. Okay, so let's start walking through this circuit now. So we're going to start, let's see where we're going to start. Doesn't really matter. Either one I think is going to give us negative voltage. So we're going to start here, and we've got 2.8 volts, right? But we got negative 2.8 because we're going against the arrow here. Then we've got a positive 120 plus positive 120. So in this case, we have 240 volts minus the 2.8, and we're expecting to see a voltage of 32 volts. Okay, if we go in the opposite direction from this connection here, then again, we're going against the arrow. So we're going negative 120, so now we got negative 240, and then we got a positive 2.8. So again, the difference between the 240 that we're seeing down here and the 2.8 up here should result in a voltage of 32 volts. So this is the buck connection, or the subtractive connection, in that the voltages are going to subtract from each other. All right, let's see if we get that in the lab, guys. Okay, so we're fairly confident that we've got all the winding terminals labeled properly now. Let's do the subtractive connection now. So I'm going to turn the power off, and I've got this jumper here, which I'm going to remove. I'm going to keep, let me take my connections out for the meter here. I'm going to keep this jumper between X2 and X3. And now the jumper that I'm going to put from the primary to the secondary, the previous one I had was X1 to H2. Now I'm going to do X1 to H1. So X1 to H1. Okay, so now this is going to be the subtractive polarity, in that this voltage is going to be subtracted from this voltage here. So the secondary voltages are going to be 240, primary voltage is going to be 2.8. You're going to see the difference between those two voltages now when I go between the two open connections. What are the two open connections? Well, it looks like I have an open connection clearly here at X4, and the other open connection here is H2. It's not open in that it has a connection to the source, but I don't have an additional connector there. Okay, so I'm going to turn this on, and we should see the lower voltage now. So I got 40 volts, right? We were expecting the difference between 240 and 2.8 was at 32 volts. And again, we're seeing 40 volts there for the subtractive connection. So we've now seen that on the primary, let me show you that. On the primary, we're seeing 208 volts. On the secondaries, we should be seeing 120 volts. I'm not sure if I showed you that, but let me show you that right here. So this was seen before. This is our source voltage of 208 volts. Okay, and then each of these windings are giving us 120 volts. Okay, 124. But if we put a load on that, it would go down to 120. Remember that your open circuit voltage is always higher than when you put a load on. Second winding here will also be identical at 124. So we're confident now on the connections for the secondary of this transformer, in that we now know that this one's H1, H2, that's clearly shown, but now we know that this is X1, X2, X3, and then X4. Okay, let's try the next transformer. We have to do the same test on each of the transformers. Now, knowing that this was the connection for the first transformer, most likely it's going to be the same for this guy. I don't think we're that cruel to randomize them, but we'll find out in 2 seconds. So let's move this power down to the second transformer. You're seeing that I'm keeping the polarity exactly the same on the primary there. If I flip that, then I mess everything up on the secondary side. I flip everything on the secondary side. I want the primary voltage polarity to be the same all the way through these tests. Okay. Next thing we're going to do is we'll check out the voltage. So again, we'll see here on our primary, we'll have 2.8. Okay. Now again, this voltage changes day to day depending on what loads are on the rest of the floor. There's a big compressor that turns on. Sometimes the voltage goes down to 207, sometimes down to 206, sometimes it's 209, but today it's a gorgeous 208. Okay, on the secondary here, we should have 124 volts. Okay, again, it's not 120 because it doesn't have a load on it. It's always a higher voltage without a load. We should see identical voltage here on this guy. Beautiful. Okay, so those guys are good. Okay, now you'll see that my hands are nowhere near the circuit there. in that I'm not actually holding the meter leads. I have the same connections or same jumpers that I'm using that go to the meter, so I don't have to have my hands in the circuit at any point there. Okay, next thing we're going to do is we're going to put that jumper back in. So we're going to series up the secondary winding. So I'm going to do X2, what I think is X2, and X3 there. Okay, and then for the additive voltage or the boost connection is always X1 to H2. Okay, so I'm going to connect up X1 to H2. Okay, I've now seriesed up this primary and all the secondary windings there. So I've created what's similar to an auto transformer in that there's no disconnect now between the primary and the secondary. This, I believe, is my additive voltage. So now when I go between X4, what I think is X4, and H1, so those are my open connections there, then I should see the higher voltage being developed on the meter. Nice, right on. Okay, so it looks like, with confidence, this one's probably going to be the same here because we've done the same connections as the previous transformer, and we're seeing the additive voltage, 2.8 plus the 240 there. Okay, why is it not exactly 448? Because there is no load connected to this, and the voltage on transformers without a load, without current actually flowing, is higher because you don't have any current flowing through these windings. So the internal resistance of the windings isn't coming into play at this point. Let's take a look at the subtractive voltage now. Subtractive voltage is always H1 to X1. Sorry, I had a brain fart. So H1 to X1. So I'm going to take this guy. So I'm taking the meter out of the circuit here. I'm moving it from X1 to H2. From X1, I'm going to go to H1 now. So I'm going to the opposite connection of the primary winding. Okay, I'm taking a voltage of the external connections that are open. Okay, I have not shorted out the transformer. A little bit of glare on the meter here. Okay, so let's take a look at this voltage. This voltage should, in theory, be 32 volts, the difference between 240 and 2.8, but we're seeing 40 volts because we don't have a load connected. Nice. Okay, if we had screwed this up, then, so let's show that one more time. So if we had screwed this up, then, just taking all my connections out for the meter, then I would have thought this was 3 like I did before, right? So if that's the case, and I take I'm going to go back to the additive voltage, right? So H2 to X1, then when I take this voltage between the two open terminals, then these two voltages are going to cancel out, and I'm going to be left with the voltage on the supply on the primary there. So we should see 2.8 volts on the meter. So that's not X4, that's not X3, it's actually X4. Okay, so hopefully everything's cool so far and that you're following me. I'm going to do one more. 3 times usually is a good point to hammer things through, so nice that we have 3 separate times that we're doing this. Okay, if you're lost, then go back in the video and take a look at the diagrams that I showed you for each of the connections for the additive, the subtractive, and then messing up the polarity of one of the windings here. Okay, so I'm thinking that whoever wired this up kept this the same. So this guy is going to be 4, and this guy is going to be 3. Okay, so again, I'm bringing my voltage down to the 3rd transformer. I'm keeping that polarity the same. Okay, I'm now going to jumper my X2 and my X3, or what I think is X2 and what I think is X3. Okay, so same polarity to the primary means that the secondary windings are all going to be in phase. Okay, I'm not changing this polarity, and now I'm seriesing up the secondary so that I would have 120 plus 120 giving me 240 volts on the secondary side. Okay, I'm now going to do the additive voltage. So additive connection or additive polarity is always X1 to H2. Okay, so what I think is X1 to H2. Okay, now I'm going to connect my meter to the two open connections here. Okay, and you can also see, like, I don't have power, but if I was, asleep at the wheel here and did have power to the circuit, we're using shrouded leads, and so there's no point where I can actually touch anything metal, right? There's nothing grounded around me. So if I was asleep at the wheel and that was doing this live, I'm supposed to be doing it live, but we should be safe here, right? But you can see that every time that I move the connections, I have the power off here, okay? So this should be the additive voltage here. Let's take a look. Okay, beautiful. So I got 456 volts. So that means that these guys are most likely identical to these ones. Okay, let's make sure one more time. We're going to change the connection here. So I'm going to remove the meter leads here. I'm going to change the jumper. The jumper from primary to secondary is the blue conductor. So the blue conductor is now going to go from H1 over to X1, right? So I'm moving this from H2 down to H1, okay, changing the connections between the primary and the secondary. And now I'm going to take the voltage between the two open connections. I'm confident that this is the subtractive polarity and that this 240 minus the 208 should give me 32, but we've seen that it's 40 volts. Ah, yes, 40 volts, right on. Okay, and then just for giggles, because now that we're confident, we know that everything's good, right? So now we're confident we can now connect this up as a three-phase transformer. But again, just one more time, I'm going to keep this one as the additive polarity here. And then I'm going to remove my meter for 2 seconds. And then last thing I'm going to do is I'm going to just show you that if I had connected to the wrong terminal here, then between the two open connections, I should see 208 volts. There we go. Okay, so at any point if you see 208, then take one of the windings and scratch out the terminals and flip the polarity of that one winding. Okay, one of the windings is opposite from the other. Okay, so that means that this is not X3, it's actually X4. So the series connection should be between these two terminals right here. And then when I take the voltage, this is the additive voltage between H1 and X4, I should see the higher voltage from those two. Beautiful. Okay, so hopefully everything made sense, guys. And you see that we went through it nice, slowly, and methodically. First thing we did was we tested out the fuses. We made sure they were good. We put the fuses back. We made sure we were working from the 3 amp breaker. Then we checked the ohmic reading on each of the primaries, the ohmic value on each of the secondaries to make sure that a previous student had not smoked those windings. Then we connected up the power to the primary. So we put 2.8 to the primary. We saw 120, 120 on each of those guys. And then we did the additive connection in that we summed the primary and the secondary voltages together, giving us 448 volts. And then we did the subtractive polarity. We were expecting 32 volts and we got 40 volts. And at any point, if we had screwed up not that we'd screwed up, but if we were confused on the connections of one of the windings and we're seeing 2.8 volts, that means that one of the windings is canceling the other and we're only seeing the voltage that's apparent on the primary. So we scratch one out, scratch the other one out, put the opposite number there, connect it up, and make sure that the additive and the subtractive polarities are working for you. Okay, sweet. Now that we've done all these connections, we should be able to create a 3-phase bank, and all of these transformers will be in phase. So we've taken all this time to make sure that all of the windings magnetic fields are going in the same direction. That way, once we create a 3-phase delta or a 3-phase Wye, then we're going to have the appropriate voltages. All right, guys, thanks very much for your patience. Hopefully everything made sense. Any questions, put it into the comments, and hopefully you've been able to follow with the diagram, and hopefully you're now clear on the buck boost test on the transformer. If at any point you had any questions, make sure to ask your instructor, because you'll be completely messed up on the rest of the three-phase transformer connections if you have not done this properly. All right, guys, thanks for your patience. We'll see you on the next one.